Okay, so this is hypothesis test for paired t-test, scenario number 3. It's page 145 of the notes spiral. So, and this is an AP question. Investigators at the U.S. Department of Agriculture wish to compare methods of determining the level of E. coli bacterial contamination in beef. Two different methods, A and B, of determining the level of contamination were used to each of 10 randomly selected specimens. So basically what we're saying is we used both A and B on each. That means they were tested twice. Because they're tested twice, could be a paired test. Now I'm going to look ahead, continue on to see what my data looks like. All right. The data obtained in millimicrobe liters of ground beef for each of the methods are shown in the table below. So we look and we go, hey, you know what? We have data of the same length, and beef specimen 1 was tested twice. Beef cut 2 was tested twice. Beef specimen 3 was tested twice. So everything was tested twice. So this leads me to believe that we have paired data. All right, everything was tested twice, so we can use the paired data. Is there a significant difference in the mean amount of E. coli bacteria detected by the two methods for this type of beef? Provide a statistical justification to support your answer. So here's what I've done. And here's what you need to do. You need to take all that data and put it in L1 and L2. And just in case you forgot, we're going to go stat, edit, and then you're going to input the data into L1 and into L2, all 10. All right. Okay, so the very first thing we need to do is write our null hypothesis. Because we were talking about mean difference, if there's, the assumption is that there is none. The difference between the two is 0. All right. Now, they also ask, is there a significant difference? That doesn't tell me that 1 is better. That doesn't tell me that A is greater than B or less than B. It tells me that we're working with a not equal. All right. So this makes this a two-tailed test. So the mean difference does not equal 0. So let mu d equal the true population mean difference in detection methods for E. coli A minus B. I could have done B minus A, but whichever order I chose, I need to define. So I'm telling you that I'm going A minus B. And why did I do A? Because it was first. All right. Conditions, random sample. They told us that they randomly selected 10. That's good. That makes things easy. We can just say it's given. All right, then we need to check their sample size. Well, we have 10 samples divided by 0.1 is 100. So there are more than 100 pieces of beef. The sample is less than 10% of the population. That's good. Technically, the sample size is less than 10% of the population. The next thing is the new condition, which is differences are independent. Well, I'm going to bet that the detection difference in sample 1 does not impact 3, does not impact 4. So I'm going to say that there is no difference. So it's reasonable to assume that the test differences are independent. That's what we need to say, that they are independent, and that one test should not impact another. Our next is a normality. If they told us it was normal, if they told us it was normal, we would be good to go. They didn't do that. So then I need to just go, well, do I have 30 pairs or more of data? And the fact of the matter is, I don't. I only have 10 pairs. If I'd had 30 or more pairs, I could say it was normal by central limit theorem. Since I don't, I'm going to have to construct a box plot. So I have my data in L1 and L2, and I'm going to arrow up to the top of L3. I just arrowed up. I'm going to press second 1 minus second 2. It's real important that I went L1 minus L2 because I went A minus B. That's the way I defined it, so I need to go in that order. I press enter, it populates it. Then I'm going to go second stat plot, press enter, arrow to the left, drop down, arrow right until I get to the box plot that shows outliers. My X list is in L3, so second 3. And I can press zoom 9. and that's what I get. And we can argue about how symmetric it is or not, but for College Board purposes, there are no outliers, and we're going to say symmetric enough. Remember, we can use the trace feature to get the values for the major points. So the minimum value is -1, then the quartile 1 is -0.1, the median is 0.4, Q3 is at 0.7, and 1.2. Now, reality is I'm not very good at drawing scales. So I label the major points. That's good enough. And I say that the box plot is reasonably symmetric with no outliers. The distribution appears to be approximately normal. Well, for this particular type of problem, we are working with x bar d minus mu d SD divided by the square root of n. Well, we know n, in this case, is 10 because we have 10 pairs of data. Really important that it's 10, not 20. We have 10 pairs of data. Our degrees of freedom are going to be 9 in 10 minus 1. Mu d, we know to be 0. That's the hypothesis claim, but we don't have x bar d and we don't have SD yet. So to get those, I'm going to press the stat button in the middle of my calculator, edit over to L1. So now it says stat calc, one variable statistics, enter. My list is an L3, so second 3, down arrow. And I end up getting x bar equals 0.29, SD, so x bar d, and then SD equals 0.6297. All right, so now I have that values and I can go ahead and plug them in. But before I do that, I want to draw a graph of what it is I'm working with. So what I'm working with is the claim is 0. This is what the claim is. But I got a sample of 0.29. This is my x bar. And we said that it was greater than, or excuse me, we said it was not equal to. So I'm shading this way, but I also have an equal amount shaded this way. All right. So I plugged in my values, 0.29, that's my x bar d, minus 0, 0.6297 divided by the square root of 2. Technically, right here, there should be a 2 times. And you're like, well, why? Well, because I shaded to the right, that's a greater than, but my alternative hypothesis was not equal. So it needs to be 2 tails. Anytime you have a 2-tailed test, you need to multiply by 2. So there should be a 2 here. So 2 times this probability. And when I run this test, stat test, t-test, data needs to be highlighted. My mean is assumed to be 0. My data is an L3. I'm going to go ahead and calculate a not equal. When I do that, I end up getting t is 1.45. So 2 times the probability of this, and that equals 0.1793. Now it's already doubled it, so I don't need to go back and do that. So p-value is 0.1793, which is greater than an alpha. So 1,793 is greater than 500. We're going to fail to reject. But I want to go back up here and take a look at this for just a moment. I want to take a look at that for just a moment and explore that just a moment more. What if I just left it as greater than 1.456? Well, let's first run the test that way. Stat test, t-test. And let's just change it to the greater than symbol that I actually have shown. Now I get 0.0896. Well, let's take a moment. 0.0896. I multiply that by 2. Then we get our actual one that we're supposed to have. So this is why I have to put the 2 times in there, because I'm working with a greater than. And some people go, well, why don't you use a not equal symbol? Well, not equal means it could be any value not 1.456. I actually need a direction. So this is why I have to do 2 times the actual direction. Okay. So our decision was to fail to reject because 0.1793 was greater than 0.05. So we fail to reject. There is not sufficient evidence at alpha equal 0.05 to suggest that the true population mean difference in detection methods for E. coli is different than 0. Not greater than 0, not less than 0, different, because that was what our alternative hypothesis says. So there is no statistical differences between the two methods. And you're like, well, wait a second. I know that there's some because there's 0.29. And the answer is yes. But there's about an 18% chance that you get a value as extreme as this or more extreme from a random sample. And that's not that rare. We consider rare to be less than 5%. 5% or less we consider rare. So we're going to say 18% is not rare enough. So we're going to say that there's not sufficient statistical differences. There actually is, there appears to be a little bit from our sample, but it's not large, it's not different enough to be considered statistically significant. It could happen too easily by random chance alone. All right, the next one will be on the same data, but it will be a confidence interval.